information via a path and a generic function. Joe goes to the whiteboard. He draws a diagram like that in figure 3.5, which shows the catalog data as a tree. Joe: You see, Theo, each piece of information is accessible via a path made of strings and integers. For example, the path of Alan Moore's first book is this. Section 3.4, Calculating Search Results. Theo: Interesting. I'm starting to feel the power of expression of DOP. Joe: Wait, that's just the beginning. Let me show you how simple it is to write code that retrieves book information and displays it in search results. Can you tell me exactly what information has to appear in the search results? Theo: Searching for book information should return ISBN, title, and author names. Joe: And what would a book info record look like for Watchmen? Theo quickly enters the code on his laptop. He then shows it to Joe. Joe: Now I'll show you step by step how to write a function that returns search results matching a title in JSON format. I'll use generic data manipulation functions from Lodash. Theo: I'm ready. Joe: Let's start with an author names function that calculates the author names of a book record by looking at the authors by ID index. Could you tell me what's the information path for the name of an author whose ID is author ID? Theo: It's this. Joe: Now let me show you how to retrieve the name of several authors using _.map. Joe types the code to map the author IDs to the author names. Theo nonchalantly peeks over Joe's shoulder. Theo: What's this _.map function? It smells like functional programming. You said I wouldn't have to learn FP to implement DOP. Joe: No need to learn functional programming in order to use _.map, which is a function that transforms the values of a collection. You can implement it with a simple for loop. Theo spends a couple of minutes in front of his computer figuring out how to implement _.map. Now he's got it. After testing Theo's implementation of map, Joe shows Theo the test. Joe again compliments Theo. Joe: Well done. Theo: You were right. It wasn't hard. Joe: Now let's implement author names using _.map. It takes a few minutes for Theo to come up with the implementation of author names. When he's finished, he turns his laptop to Joe. Joe: We also need a book info function that converts a book record into a book info record. Let me show you the code for that. Theo: Looking at the code, I see that a book info record has 3 fields: title, ISBN, and author names. Is there a way to get this information without looking at the code? Joe: You can either add it to the data entity diagram or write it in the documentation of the book info function, or both. Theo: I have to get used to the idea that in DOP, the record field information is not part of the program. Joe: Indeed, it's not part of the program, but it gives us a lot of flexibility. Theo: Is there any way for me to have my cake and eat it too? Joe: Yes, and someday I'll show you how to make record field information part of a DOP program. See chapters 7 and 12. Theo: Sounds intriguing. Joe: Now that we have all the pieces in place, we can write our search books by title function, which returns the book information about the books that match the query. First, we find the book records that match the query with _.filter, and then we transform each book record into a book info record with _.map and book info. Theo: You're using Lodash functions without any explanation again. Joe: Sorry about that. I'm so used to basic data manipulation functions that I consider them as part of the language. What functions are new to you? Theo: _.values and _.filter. Joe: Well, _.values returns a collection made of the values of a map, and _.filter returns a collection made of the values that satisfy a predicate. Theo, _.values seems trivial. Let me try to implement _.filter. The implementation of _.filter takes a bit more time. Eventually, Theo manages to get it right. Then he is able to test it. Theo, to me, it's a bit weird that to access the title of a book record, I need to write _.get of book and string title. I'd expect it to be book.title in dot notation, or book of string title in brackets in bracket notation. Joe, remember that book is a record that's not represented as an object. It's a map. Indeed, in JavaScript, you can write _.get of book and string title, book.title, or book of string title in brackets. But I prefer to use Lodash's _.get function. In some languages, the dot and the bracket notations might not work on maps. Theo, being language agnostic has a price. Joe, right. Would you like to test search books by title? Theo, absolutely. Let me call search books by title to search the books whose title contain the string watch. Theo, it seems to work. Are we done with the search implementation? Joe, almost. The search books by title function we wrote is going to be part of the catalog module, and it returns a collection of records. We have to write a function that's part of the library module, and that returns a JSON string. Theo, you told me earlier that JSON serialization was straightforward in DOP. Joe, correct. The code for search books by title JSON retrieves the catalog record, passes it to search books by title, and converts the results to JSON with json.stringify. That's part of JavaScript. Here, let me show you. Joe, in order to test our code, we need to create a library record that contains our catalog record. Could you do that for me, please? Theo, should the library record contain all the library fields, name, address, and user management? Joe, that's not necessary. For now, we only need the catalog field, then the test for searching books. Theo, how are we going to combine the 4 functions that we've written so far? Joe, the functions author names, book info, and search books by title go into the catalog module, and search books by title JSON goes into the library module. Theo looks at the resulting code of the 2 modules, library and catalog. He's quite amazed by its conciseness. After testing the final code in listing 3.24, Theo looks again at the source code from listing 3.23. After a few seconds, he feels like he's having another aha moment. Theo, the important thing is not that the code is concise, but that the code contains no abstractions. It's just data manipulation. Joe responds with a smile that says, "You got it, my friend." Joe, it reminds me of what my first meditation teacher told me 10 years ago. Meditation guides the mind to grasp the reality as it is, without the abstractions created by our thoughts. Tip. In DOP, many parts of our codebase tend to be just about data manipulation with no abstractions. Section 3.5. Handling records of different types. We've seen how DOP enables us to treat records as first-class citizens that can be manipulated in a flexible way using generic functions. But if a record is nothing more than an aggregation of fields, how do we know what the type of the record is? DOP has a surprising answer to this question. Theo, I have a question. If a record is nothing more than a map, how do you know the type of the record? Joe, that's a great question with a surprising answer. Theo, I'm curious. Joe, most of the time, there is no need to know the record type. Theo, what? What do you mean? Joe, I mean that what matters most are the values of the fields. For example, take a look at the catalog.authornames source code. It operates on a book record. but the only thing that matters is the value of the author IDs field. Doubtful. Theo looks at the source code for catalog.author names. This is what Theo sees. Theo, what about differentiating between various user types like member versus librarian? I mean, they both have email and encrypted password. How do you know if a record represents a member or a librarian? Joe, simple. You check to see if the record is found in the librarians by email index or in the members by email index of the catalog. Theo, could you be more specific? Joe, sure. Let me write what the user management data of our tiny library might look like, assuming we have one librarian and one member. To keep things simple, I'm encrypting passwords through naive base 64 encoding for the user management record. Tip. Most of the time, there's no need to know the record type. Theo, this morning you told me you'd show me the code for usermanagement.isLibrarian function this afternoon. Joe, so here we are. It's afternoon and I'm going to fulfill my promise. Joe implements isLibrarian. With a slight pause, he then issues the test for isLibrarian. Theo, I'm assuming that _.has is a function that checks whether a key exists in a map, right? Joe, correct. Theo, okay, you simply check whether the librarians by email map contains the email field. Joe, yep. Theo, would you use the same pattern to check whether a member is a super member or a VIP member? Joe, sure. We could have super members by email and VIP members by email indexes, but there's a better way. Theo, how? Joe, when a member is a VIP member, we add a field isVIP with the value true to its record. To check if a member is a VIP member, we check whether the isVIP field is set to true in the member record. Here's how I would code isVIP member. Theo, I see that you access the isVIP field via its information path, array of string members by -email, variable email, string isVIP. Joe, yes, I think it makes the code crystal clear. Theo, I agree. I guess we can do the same for isSuperMember and set an isSuper field to true when a member is a supermember. Joe, yes, just like this. Joe assembles all the pieces in a user management class. He then shows the code to Theo. Theo looks at the user management module code for a couple of seconds. Suddenly, an idea comes to his mind. Theo, why not have a type field in member record whose value would be either VIP or super? Joe, I assume that according to the product requirements, a member can be both a VIP and a super member. Theo, then the types field could be a collection containing VIP or super or both. Joe, in some situations, having a types field is helpful, but I find it simpler to have a Boolean field for each feature that the record supports. Theo, is there a name for fields like isVIP and isSuper? Joe, I call them feature fields. Tip. Instead of maintaining type information about a record, use a feature field, for example, isVIP. Theo, can we use feature fields to differentiate between librarians and members? Joe, you mean having an isLibrarian and an isMember field? Theo, yes, and having a common user record type for both librarians and members. Joe, we can, but I think it's simpler to have different record types for librarians and members, librarian for librarians, and member for members. Theo, why? Joe, because there's a clear distinction between librarians and members in terms of data. For example, members can have book lendings, but librarians don't. Theo, I agree. Now we need to mention the two member feature fields in our entity diagram. With that, Theo adds these fields to his diagram on the whiteboard. When he's finished, he shows Joe his additions. Figure 3.6. Joe, do you like the data model that we have designed together? Theo, I find it quite simple and clear. Joe, that's the main goal of DOP. Theo, also, I'm pleasantly surprised how easy it is to adapt to changing requirements, both in terms of code and the data model. Joe, I suppose you're also happy to get rid of complex class hierarchy diagrams. Theo, absolutely. Also, I think I've found an interesting connection between DOP and meditation. Joe, really? Theo, when we were eating at Simple, you told me that meditation helped you experience reality as it is without the filter of your thoughts. Joe, right? Theo, from what you taught me today, I understand that in DOP we are encouraged to treat data as data without the filter of our classes. Joe, clever. I never noticed that connection between those two disciplines that are so important for me. I guess you'd like to continue your journey in the realm of DOP. Theo, definitely. Let's meet again tomorrow. Joe, unfortunately, tomorrow I'm taking my family to the beach to celebrate the 12th birthday of my eldest daughter, Aurelia. Theo, happy birthday, Aurelia. Joe, we could meet again next Monday, if that's okay with you. Theo, with pleasure. Summary. DOP principle number 2 is to represent data entities with generic data structures. We refer to maps that have strings as keys as string maps. Representing data as data means representing records with string maps. By positional collection, we mean a collection where the elements are in order, like a list or an array. A positional collection of strings is noted as string in brackets. By index, we mean a collection where the elements are accessible via a key, like a hash map or a dictionary. An index of books is noted as book in braces. In the context of a data model, the index keys are always strings. A record is a data structure that groups together related data items. It's a collection of fields, possibly of different data types. A homogeneous map is a map where all the values are of the same type. A heterogeneous map is a map where the values are of different types. In DOP, we represent a record as a heterogeneous string map. A data entity diagram consists of records whose values are either primitives, positional collections, or indexes. The relation between records in a data entity diagram is either composition or association. The data part of a DOP system is flexible, and each piece of information is accessible via its information path. There is a trade-off between flexibility and safety in a data model. DOP compromises on data safety to gain flexibility and genericity. In DOP, the data model is flexible. We're free to add, remove, and rename record fields dynamically at runtime. We manipulate data with generic functions. Generic functions are provided either by the language itself or by third-party libraries like Lodash. JSON serialization is implemented in terms of a generic function. On the one hand, we've lost the safety of accessing record fields via members defined at compile time. On the other hand, we've liberated data from the limitation of classes and objects. Data is represented as data. The weak dependency between code and data makes it easier to adapt to changing requirements. When data is represented as data, it is straightforward to visualize system data. Usually, we do not need to maintain type information about a record. We can visualize any part of the system data. In statically typed languages, we sometimes need to statically cast the field values. Instead of maintaining type information about a record, we use a feature field. There is no significant performance hit for accessing a field in a map instead of a class member. In DOP, you can retrieve every piece of information via an information path and a generic function. In DOP, many parts of our code base tend to be just about data manipulation with no abstractions. Chapter 4. State Management. Time Travel. This chapter covers a multi-version approach to state management, the calculation phase of a mutation, the commit phase of a mutation, keeping a history of previous state versions. So far, we have seen how DOP handles queries via generic functions that access system data, which is represented as a hash map. In this chapter, we illustrate how DOP deals with mutations, requests that change the system state. Instead of updating the state in place, we maintain multiple versions of the system data. At a specific point in time, the system state refers to a specific version of the system data. This chapter is a deep dive in the third principle of DOP. Principle number 3. Data is immutable. The maintenance of multiple versions of the system data requires the data to be immutable. This is made efficient both in terms of computation and memory via a technique called structural sharing, where parts of the data that are common between two versions are shared instead of being copied. In DOP, a mutation is split into two distinct phases. In the calculation phase, we compute the next version of the system data. In the commit phase, we move the system state forward so that it refers to the version of the system data computed by the calculation phase. This distinction between calculation and commit phases allows us to reduce the part of our system that is stateful to its bare minimum. Only the code of the commit phase is stateful, while the code in the calculation phase of a mutation is stateless and is made of generic functions similar to the code of a query. The implementation of the commit phase is common to all mutations. As a consequence, inside the commit phase, we have the ability to ensure that the state always refers to a valid version of the system data. Another benefit of this state management approach is that we can keep track of the history of previous versions of the system data. Restoring the system to a previous state, if needed, becomes straightforward. Table 4.1 shows the two phases. In this chapter, we assume that no mutations occur concurrently in our system. In the next chapter, we will deal with concurrency control. Section 4.1. Multiple versions of the system data. When Joe comes into the office on Monday, he tells Theo that he needs to exercise before starting to work with his mind. Theo and Joe go for a walk around the block, and the discussion turns toward version control systems. They discuss how Git keeps track of the whole commit history and how easy and fast it is to restore the code to a previous state. When Theo tells Joe that Git's ability to time travel reminds him of one of his favorite movies, Back to the Future, Joe shares that a month ago he watched the Back to the Future trilogy with Nariah, his 14-year-old son. Their walk complete, they arrive back at Theo's office. Theo and Joe partake of the espresso machine in the kitchen before they begin today's lesson. Joe: So far, we've seen how we manage queries that retrieve information from the system in DOP. Now I'm going to show you how we manage mutations. By a mutation, I mean an operation that changes the state of the system. Note: a mutation is an operation that changes the state of the system. Theo: Is there a fundamental difference between queries and mutations in DOP? After all, the whole state of the system is represented as a hash map. I could easily write code that modifies part of the hash map, and it would be similar to the code that retrieves information from the hash map. Joe: You could mutate the data in place, but then it would be challenging to ensure that the code of a mutation doesn't put the system into an invalid date. You would also lose the ability to track previous versions of the system state. Theo: I see. So how do you handle mutations in DOP? Joe: We adopt a multi-version state approach, similar to what a version control system like Git does. We manage different versions of the system data. At a specific point in time, the state of the system refers to a version of the system data. After a mutation is executed, we move the reference forward. Theo: I'm confused. Is the system state mutable or immutable? Joe, the data is immutable, but the state reference is mutable. Tip. The data is immutable, but the state reference is mutable. Noticing the look of confusion on Theo's face, Joe draws a quick diagram on the whiteboard. He then shows Theo figure 4.1, hoping that it will clear up Theo's perplexity. Theo, does that mean that before the code of a mutation runs, we make a copy of the system data? Joe, no, that would be inefficient, as we would have to do a deep copy of the data. Theo, how does it work then? Joe, it works by using a technique called structural sharing, where most of the data between subsequent versions of the state is shared instead of being copied. This technique efficiently creates new versions of the system data, both in terms of memory and computation. Theo, I'm intrigued. Tip. With structural sharing, it's efficient in terms of memory and computation to create new versions of data. Joe, I'll explain in detail how structural sharing works in a moment. Theo takes another look at the diagram in figure 4.1, which illustrates how the system state refers to a version of the system data. Suddenly, a question emerges. Theo, are the previous versions of the system data kept? Joe, in a simple application, previous versions are automatically removed by the garbage collector. But in some cases, we maintain historical references to previous versions of the data. Theo, what kind of cases? Joe, for example, if we want to support time travel in our system, as in Git, we can move the system back to a previous version of the state easily. Theo, now I understand what you mean by data is immutable, but the state reference is mutable. Section 4.2, Structural Sharing. As mentioned in the previous section, structural sharing enables the efficient creation of new versions of immutable data. In DOP, we use structural sharing in the calculation phase of a mutation to compute the next state of the system based on the current state of the system. Inside the calculation phase, we don't have to deal with state management. That is delayed to the commit phase. As a consequence, the code involved in the calculation phase of a mutation is stateless and is as simple as the code of a query. Theo, I'm really intrigued by this more efficient way to create new versions of data. How does it work? Joe, let's take a simple example from our library system. Imagine that you want to modify the value of a field in a book in the catalog. For instance, the publication year of Watchmen. Can you tell me the information path for Watchmen's publication year? Theo takes a quick look at the catalog data in figure 4.2. Then he answers Joe's question. Theo, the information path for Watchmen's publication year is this. Joe, now let me show you how to use the immutable function _.set that Lodash also provides. Theo, wait, what do you mean by an immutable function? When I looked at the Lodash documentation for _.set on their website, it said that it mutates the object. Joe, you're right, but the default Lodash functions are not immutable. In order to use an immutable version of the functions, we need to use the Lodash FP module as explained in the Lodash FP guide. Note: see this link to view Lodash's documentation for _.set, and see this link to view the Lodash FP guide. Theo, do the immutable functions have the same signature as the mutable functions? Joe, by default, the order of the arguments in immutable functions is shuffled. The Lodash FP guide explains how to resolve this. With this piece of code, the signature of the immutable functions is exactly the same as the mutable functions. Tip: in order to use Lodash immutable functions, we use Lodash's FP module, and we configure it so that the signature of the immutable functions is the same as in the Lodash documentation website. Theo, so basically I can still rely on Lodash documentation when using immutable versions of the functions. Joe, except for the piece in the documentation that says the function mutates the object. Theo, of course. Joe, Now I'll show you how to write code that creates a version of the library data with the immutable function _.set. Joe's fingers fly across Theo's keyboard. Theo then looks at Joe's code, which creates a version of the library data where the Watchman publication year is set to 1986. Note: a function is said to be immutable when, instead of mutating the data, it creates a new version of the data without changing the data it receives. Theo, you told me earlier that structural sharing allowed immutable functions to be efficient in terms of memory and computation. Can you tell me what makes them efficient? Joe, with pleasure, but before that, you have to answer a series of questions. Are you ready? Theo, yes, sure. Joe, what part of the library data is impacted by updating the Watchman publication year, the user management or the catalog? Theo, only the catalog. Joe, what part of the catalog? Theo, only the Books by ISBN index. Joe, what part of the Books by ISBN index? Theo, only the book record that holds the information about Watchman. Joe, what part of the book record? Theo, only the publication year field. Joe, perfect. Now, suppose that the current version of the library data looks like this. Joe goes to the whiteboard and draws a diagram. Figure 4.3 shows the result. Theo, so far so good. Joe, next, let me show you what an immutable function does when you use it to create a new version of library, where the publication year of Watchman is set to 1986 instead of 1987. Joe updates his diagram on the whiteboard. It now looks like figure 4.4. Theo, could you explain? Joe, the immutable function creates a fresh library hash map, which recursively uses the parts of the current library that are common between the two versions instead of deeply copying them. Theo, it's a bit abstract for me. Joe, the next version of library uses the same user management hash map as the old one. The catalog inside the next library uses the same authors by ID as the current catalog. The Watchman book record inside the next catalog uses all the fields of the current book, except for the publication year field. Theo, so in fact, most parts of the data are shared between the two versions, right? Joe, exactly. That's why this technique is called structural sharing. Tip: structural sharing provides an efficient way, both in terms of memory and computation, to create a new version of the data by recursively sharing the parts that don't need to change. Theo, that's very cool. Joe, indeed. Now let's look at how to write a mutation for adding a member using immutable functions. Once again, Joe goes to the whiteboard. Figure 4.5 shows the diagram that Joe draws to illustrate how structural sharing looks when we add a member. Theo, awesome! The catalog and the librarian's hash maps don't have to be copied. Joe, now in terms of code, we have to write a library.addMember function that delegates to usermanagement.addMember. Theo, I guess it's going to be similar to the code we wrote earlier to implement the search books query, where library.searchBooksByTitle.json delegates to catalog.searchBooksByTitle. Joe, similar in the sense that all the functions are static, and they receive the data they manipulate as an argument. But there are two differences. First, a mutation could fail, for instance, if the member to be added already exists. Second, the code for library.addMember is a bit more elaborate than the code for library.searchBooksByTitle.json, because we have to create a new version of library that refers to the new version of user management. Here, let me show you an example. Theo, to me, it's a bit weird that immutable functions return an updated version of the data instead of changing it in place. Joe, it was also weird for me when I first encountered immutable data in Clojure 7 years ago. Theo, how long did it take you to get used to it? Joe, a couple of weeks. Section 4.3. Implementing structural sharing. When Joe leaves the office, Theo meets Dave near the coffee machine. Dave looks perplexed. Dave, who's the guy that just left the office? Theo, it's Joe, my DOP mentor. Dave, what's DOP? Theo, DOP refers to data-oriented programming. Dave, I never heard that term before. Theo, it's not well known by programmers yet, but it's quite a powerful programming paradigm. From what I've seen so far, it makes programming much simpler. Dave, can you give me an example? Theo, I just learned about structural sharing and how it makes it possible to create new versions of data effectively without copying. Dave, how does that work? Theo takes Dave to his office and shows him Joe's diagram on the whiteboard. See Figure 4.6. It takes Theo a few minutes to explain to Dave what it does exactly, but in the end, Dave gets it. Dave, what does the implementation of structural sharing look like? Theo, I don't know. I used the _.set function from Lodash. Dave, it sounds like an interesting challenge. Theo, take the challenge if you want. Right now, I'm too tired for this recursive algorithmic stuff. The next day, Theo stops by Dave's cubicle before heading to his office. Dave, with a touch of pride, shows Theo his implementation of structural sharing. Theo is amazed by the fact that it's only 11 lines of JavaScript code. Theo, Dave, you're brilliant. Dave, smiling, aw, shucks. Theo, oops, I have to go. I'm already late for my session with Joe. Joe is probably waiting in my office, biting his nails. Section 4.4. Data Safety. Joe is about to start the day's lesson. Theo asks him a question about yesterday's material instead. Theo, something isn't clear to me regarding this structural sharing stuff. What happens if we write code that modifies the data part that's shared between the two versions of the data? Does the change affect both versions? Joe, could you please write a code snippet that illustrates your question? Theo starts typing on his laptop. He comes up with this code to illustrate modifying a piece of data shared between two versions. Theo, my question is, what is the value of isBlocked in updated member? Joe, the answer is that mutating data via the native hashmap setter is forbidden. All the data manipulation must be done via immutable functions. Note: all data manipulation must be done with immutable functions. It is forbidden to use the native hashmap setter. Theo, when you say forbidden, you mean that it's up to the developer to make sure it doesn't happen, right? Joe, exactly. Theo, is there a way to protect our system from a developer's mistake? Joe, yes, there is a way to ensure the immutability of the data at the level of the data structure. It's called persistent data structures. Theo, are persistent data structures also efficient in terms of memory and computation? Joe, actually, the way data is organized inside persistent data structures make them even more efficient than immutable functions. Tip: persistent data structures are immutable at the level of the data. There is no way to mutate them, even by mistake. Theo, are the libraries providing persistent data structures? Joe, definitely. I just happen to have a list of those libraries on my computer. Joe, being well organized for a programmer, quickly brings up his list. He shows it to Theo. Immutable.js in JavaScript at immutable-js.com. Paguro in Java at github.com/GlennKPeterson/Paguro. Immutable collections in C# at this link. Persistent in Python at github.com/tobgu/persistent. Hamster in Ruby at github.com/hamstergem/hamster. Theo, why not use persistent data structures instead of immutable functions? Joe, the drawback of persistent data structures is that they are not native. This means that working with them requires conversion from native to persistent and from persistent to native. Theo, what approach would you recommend? Joe, if you want to play around a bit, then start with immutable functions. But for a production application, I'd recommend using persistent data structures. Theo, too bad the native data structures aren't persistent. Joe, that's one of the reasons why I love Clojure. The native data structures of the language are immutable. Section 4.5. The commit phase of a mutation. So far, we saw how to implement the calculation phase of a mutation. The calculation phase is stateless in the sense that it doesn't make any change to the system. Now let's see how to update the state of the system inside the commit phase. Theo takes another look at the code for library.addMember. Something bothers him. This function returns a new state of the library that contains an additional member, but it doesn't affect the current state of the library. Theo, I see that library.addMember doesn't change the state of the library. How does the library state get updated? Joe, that's an excellent question. Library.addMember deals only with data calculation and is stateless. The state is updated in the commit phase by moving forward the version of the state that the system state refers to. Theo, what do you mean by that? Joe, here's what happens when we add a member to the system. The calculation phase creates a version of the state that has two members. Before the commit phase, the system state refers to the version of the state with one member. The responsibility of the commit phase is to move the system state forward so that it refers to the version of the state with two members. Tip. The responsibility of the commit phase is to move the system state forward to the version of the state returned by the calculation phase. Joe draws another illustration on the whiteboard, figure 4.7. He hopes it helps to clear up any misunderstanding Theo may have. Theo, how is this implemented? Joe, the code is made of two classes, System, a singleton stateful class that implements the mutations, and System State, a singleton stateful class that manages the system state. Theo, it sounds to me like classic OOP. Joe, right, and this part of the system being stateful is OOP-like. Theo, I'm happy to see that you still find some utility in OOP. Joe, meditation taught me that every part of our universe has a role to play. Theo, nice. Could you show me some code? Joe, sure. Joe thinks for a moment before starting to type. He wants to show the system class and its implementation of the addMember mutation. Theo, what does system state look like? Joe, I had a feeling you were going to ask that. Here's the code for the system state class, which is a stateful class. Theo, I don't get the point of system state. It's a simple class with a getter and a commit function, right? Joe, in a moment, we are going to enrich the code of the systemstate.commit method so that it provides data validation and history tracking. For now, the important thing to notice is that the code of the calculation phase is stateless and is decoupled from the code of the commit phase, which is stateful. Tip. The calculation phase is stateless. The commit phase is stateful. Section 4.6. Ensuring system state integrity. Theo, something still bothers me about the way functions manipulate immutable data in the calculation phase. How do we preserve data integrity? Joe, what do you mean? Theo, in OOP, data is manipulated only by methods that belong to the same class as the data. It prevents other classes from corrupting the inner state of the class. Joe, could you give me an example of an invalid state of the library? Theo, for example, imagine that the code of a mutation adds a book item to the book lendings of a member without marking the book item as lent in the catalog. Then the system data would be corrupted. Joe, in DOP, we have the privilege of ensuring data integrity at the level of the whole system, instead of scattering the validation among many classes. Theo, how does that work? Joe, the fact that the code for the commit phase is common to all the mutations allows us to validate the system data in a central place. At the beginning of the commit phase, there is a step that checks whether the version of the system state to be committed is valid. If the data is invalid, the commit is rejected. Here, let me show you. Theo, it sounds similar to a commit hook in Git. Joe, I like your analogy. Theo, why are you passing the previous state in previous and the next state in next to systemValidity.validate? Joe, because it allows systemValidity.validate to optimize the validation in terms of computation. For example, we could validate just the data that is changed. Tip. In DOP, we validate the system data as a whole. Data validation is decoupled from data manipulation. Theo, what does the code of systemValidity.validate look like? Joe, someday I will show you how to define a data schema and to validate that a piece of data conforms to a schema. Note, see chapters 7 and 12 to see how Joe defines this data schema. Section 4.7, Restoring Previous States. Another advantage of the multi-version state approach with immutable data that is manipulated via structural sharing is that we can keep track of the history of all the versions of the data without exploding the memory of our program. It allows us, for instance, to restore the system back to an earlier state easily. Theo, you told me earlier that it was easy to restore the system to a